All right, we are covering section 5.8 here. So 5.8, this is all about exponential growth and decay models. So these are all based off this exponential equation P of t equals P naught e to the kt. And for this expression here, symbol P is 0. This is the initial population or amount. The symbol K. If K is positive, this is the relative rate of growth, or sometimes called decay. If K is negative, then it's a decay problem. T is time. And P of t, this is the population or amount at time t. So we're going to, first of all, this section starts out with some problems that are kind of, I guess, Algebra 2 style problems, and then we get into some calculus aspects of stuff. So we'll just start there and keep going. So for our first example here from our book, we got there's bacteria that have a growth rate. So there's a population of bacteria have growth rate, and they give us K equals 0.41, and we say assume there's 1,000 bacteria at time equals 0. And then what they want us to do is part A, they want us to, basically build a model for the situation. Then once we get our model down, part B, they want us to find the population after 5 hours. And then part C, they want us to figure out when is the population 10,000. Okay, so for part A, we have our equation. P of t equals P naught e to the kt. So what they've told me is, they've told me that the P of t equation, the initial amount was 1,000, so we had 1,000 bacteria initially. K is 0.41, and then that's all multiplied by t. So this right here is going to be our starting equation. So for part A, this will be the equation that models the problem here. For part B, they want us to find the population at t equals 5. We're going to have to use a calculator to get that. So we'll say, all right, when t is 5, what we're going to do is we're just going to plug in 5 for t right here. So we get 1,000 e to the 0.41 multiplied by 5. And we'll see what that's about equal to. Oops. E to the 0.41 times 5. And that gives us 776. And I'm going to round up since it's bacteria. We're not supposed to cut them in half. So we'll say 7768 bacteria. This will be how many bacteria are present at t equals 5. So this is our answer to part B. And then for part C, we want to know when is the population 10,000. So I take my starting equation here. And I set it equal to 10,000. And I start trying to solve for t. So step 1, I divide both sides by 1,000. So it cancels over here. 10,000 divided by 1,000 is 10. So I get 10 equals e to the 0.41t. Take natural log next. Do that to undo the e. So I get natural log of 10 is 0.41 t. So to get t completely by itself, I divide by 0.41. And I get that is my statement there. So natural log of 10 divided by 0.41. This is about 5.6 hours, about equal to t. So I guess we should round to three decimal places like they do on the AP test. So it'd be 5.616 hours. It's about equal to t. Okay, so that is our first example. So now what we're basically going to do is they're going to tell us that got a theorem here about a differential equation. So theorem. We say if y of t is a differentiable function satisfying differential equation. And the differential equation they give us is y prime equals k times y. So if you are a y value that satisfies this function right here, or sorry, satisfies this equation right here, then the function has to have the following form. Y of t equals p naught e to the kt, where p naught is the initial value p naught equals y evaluated at 0. So basically, if you have a differential equation of the form y prime equals a constant times y, then that form that we had, p naught e to the kt, that will be your y of t function, and p naught will be the initial condition on that. So we want to use a theorem, or want to solve a problem that uses this theorem. So for this example here, we want to find all solutions of y prime equals 3y, and then we want to say which solution satisfies y of 0 equals 9. Okay, so I have a function of the form y prime equals k times y. Here I have the function of the form y prime equals 3 times y. So I know that my solution will be y of t equals p naught e to the k is 3, because it's 3 times y, and here we have k times y. So it would be 3 times t. Instead of using p naught for the constant, a lot of books will also use, and our textbook does it too for this one, they use c for the constant. So instead of using p naught for the constant, our textbook switched and used c. That's pretty common, so we're going to switch over and use c like the book does. So we have this expression here, and then we're supposed to use y of 0. Y of 0 is equal to 9 to figure out the c value. So we'll say, all right, if I put 0 in for time, then y of 0 should be 9. 3 times 0 is 0. E to the 0 is 1, so this all becomes 1. And we get 9 is the c value. So this right here, sorry, I should have said it this way. This right here is our equation for all solutions. This is the general solution. So this right here is the equation. So right here's the equation for all solutions, I guess we could say. Then when c is 9, if we want to say which one satisfies this expression here, that would be y of t equals 9e to the 3t. And this is the particular one of all those solutions that satisfies that y of 0 is 9. Okay, so going to move on to a second problem based off of this stuff, and then we'll talk about a couple other examples, and then we move on to some finance stuff to finish the section out. So next little example. So they tell us penicillin leaves a person's bloodstream at a rate proportional to the amount present. So penicillin leaves bloodstream at a rate proportional to the amount present. And they're going to ask us to do a couple things. So part A, express this as a differential equation. Part B wants us to go through and say, find the decay constant. So that's the K value. Let's put a little parentheses and we'll say K. If 50 milligrams are present in the bloodstream 7 hours after initial injection of 450. Okay. Then part C, last one that we want to do, is under hypothesis of B, at what time was 200 milligrams of penicillin present? So when was 200 milligrams present? And we'll say using part B. Okay, so first of all, penicillin leaves the bloodstream at a rate proportional to the amount present. So we're going to say A prime, so the rate that penicillin is leaving the bloodstream. This will equal, it's proportional to the amount present, so K times A. This is proportional to the amount present, and it needs to be negative because the amount is leaving. So for part A, this will be the equation we want. So for part B, we have to use this information here and say, well, find the decay constant K if 50 milligrams are present 7 hours after the initial injection. So this right here is our differential equation. By the theorem, this has solution y of t equals, we could say c e to the kt. So we'll write our equation down here. Y of t, or I guess actually since we're using a for this, we should say a of t, the amount present, is going to equal c e to the negative k times t. And this is from the theorem. We're using a of t instead of y of t because the function here that we wrote down, since it's amount present, we use a. So we're finding a of t for the amount present rather than y of t that the theorem says. So now that we got this, we need to use our information here. We said, okay, initial injection of 450 was made. That tells me the c value was 450. We have e to the negative k times, they said 7 hours, so at a time of 7, the amount present is 50. So we're plugging everything into this equation here. We got the initial amount of the injection is C. When time is 7, you're down to 50 milligrams. So we plug those in, and then we need to just figure out the K value. So we'll divide by 450. Let's see here. And then what we want to do is, let's see, 50 over 450 is 1/9. This will equal e to the negative, we could say 7k. We'll take natural log of both sides. So that'll cancel. We'll get 1/9 divide by the -7. This is going to equal our k value. So I can rewrite my equation as a of t equals 400. Let's see. Divided by. So we get 400 e to the negative. The k value we found was natural log of 1/9 over -7 times t. Minus a negative is positive, so we'll rewrite this finally. Sorry, it should be 450. It was, this right here should be the initial amount that we injected, so 450. So we will have a of t equals 450 e to the natural log of 1/9 over 7 times t. So this is our equation for part B. Part B said, part B said find the decay constant, which we did, and then this will be the equation that we'll use to model part C based off of the decay constant from part B. So for part C, we found the decay constant. I guess technically part B asked us for the decay constant, which is this right here, and then part C says, hey, using part B's setup, figure out the time it takes when 200 milligrams was present. So we're going to have to use this equation here for part C. So here's the equation that we generated using part B's information. They want to know when the amount present is 200. And then we got to solve all of this for time. So we divide both sides by 450. So it'll cancel. And that'll give us 4/9 over here. So 4/9 equals e to the natural log of 1/9 over 7 times t. We apply natural log to both sides. Natural log will undo exponential base e. So we'll have natural log of 4/9 equals natural log of 1/9 over 7 times t. So if we want to get the t by itself, we have to multiply the 7 across and divide the natural log of 1/9. And so we got basically 7 natural log of 4/9 divided by natural log of 1/9. That will equal our time t. So that'll be about 2.583. Units of time on this were hours. So we'll say 2.583 hours. It's about equal to our time. The book rounded their K value, and I didn't round my K value, so that's why I left my K value in terms of the natural log. The book rounded it, so that's why our answers are slightly different from here, from what's in the book. Okay, so we're gonna pause on part 1 of the lesson here, and we'll pick up, we got doubling time, half-life, and some other stuff that we'll do in the next part.